Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Garett Brown with us today. Hey, Garett.
Hey, Frank. How are you?
Today?
It's pretty good. It's nice and sunny here today.
Where is here? Where are you at?
I'm currently in the Washington, D.C. area on vacation visiting some family, but I spend almost all of my time in Toronto.
Ah, okay. Very good. A little cooler up there. So how is, well, you can do both. So how generally has the summer been going in the northern latitudes of Toronto, and how's it going in DC?
DC has been hotter than Toronto, but and we also got the tail end of Ida.
Oh, yeah.
Yeah, it wasn't so bad where we are, but like up in the Northeast got a little bit worse. But yeah, and in Toronto, it's usually pretty nice. A little bit cooler, a little bit less humid, probably because there are fewer trees inside the city. But
yeah. Well, I'm good to hear Ida was not a too big of an issue in Washington, D.C. Let's see, it is September 2nd, 2021. I'm in Phoenix. We're actually still carrying on our monsoon season. So we got a pretty good rain last night to the desert. This is when we get our summer, is when Phoenix, the desert, gets its rain. And probably in about 2 weeks or so, if things are normal, that Gulf moisture will move back out to the Gulf of Mexico and we'll return back to the 10% level or less humidity levels.
I did my undergraduate in Utah, and I went down to Arizona a couple times, and Nevada is nice and dry there. It's nice.
Well, it's very pleasant in the winter, right? And we get a lot of Toronto snowbirds, right, coming down.
That's true.
Toronto, Canada to Phoenix in the winter, where it's very pleasant. Very cool. What is your current position in Toronto there?
Yeah, I'm a PhD student, and I work with my supervisor or advisor, Hannah Ryan.
Cool. And how far along are you in your trajectory?
It's a bit hard to say for sure. I'm in my 4th year. I've been in Toronto for 4 years, but I took a little bit of parental leave somewhere in the middle. So it's the department is very supportive and is very good. But I'm 4 years in-ish, and I have a couple years, I think, to go. Yeah.
Well, I look forward one day when we do a future video on one of your articles calling you Dr. Brown. So,
thank you. I look forward to finishing as well.
Very cool. Very cool. So Garett, what do you like to do for research?
Yeah, I really like writing code, which isn't necessarily like a research thing, but code is one of my favorite things to do. And so I really enjoy working with Professor Hannah Ryan. He's also an avid coder, with Rebound and body code and such. So working with him, focus a lot on celestial dynamics and planetary dynamics, mostly focusing on the solar system. It wasn't what my background as an undergraduate was in. I did physics, but I didn't focus on astrophysics per se. So it's quite interesting and quite fun to come into such an archaic, old field. It's just like the papers,
solar system integrations since probably Newton, right?
Yeah, a little bit by hand. But I mean, I was really inspired as a child and like a youth growing up. I grew up in Canada, but like the 55th latitude is pretty far north. And lots of strong seasons there of change between what summer is and winter is, and the kind of light and darkness that you actually get in the seasons. So I was quite inspired to like the really long nights to see the stars and the planets move around. So it was really fun. It was quite inspiring. And now it's really great to do the science and to run experiments on astrophysics. That's really fun.
Nice. And that is going to bring us to this very lovely research note. Let's see. Research note of the AAS and a repository of vanilla long-term integrations of the solar system. And Garett, take us away.
Thanks. Yeah, so I did this with my advisor, Hannah Ryan, and it was sort of at the tail end of a couple other papers that we had published in monthly notices of the Royal Astronomical Society. We had done some work on implementing high accuracy integrators into rebound with Dan Tamayo as well. I think he's currently at Princeton. And we sort of implemented some of Jack Wisdom's high order integrators. So we in part decided to take a look and see how these perform in rebound over a long period of time. So we ran a whole bunch of simulations using these high order integrators, which we can get to in a moment, but to sort of see how it performs, see how it does, and sort of like set a baseline for future projects that I've been working on. So this was sort of like our baseline test.
Cool, very nice. That's sort of your motivations there.
That's right. So we were influenced a lot by, especially the integrations by Lascar and Gastineau. And we know that Batygin and Laughlin have done also some long-term simulations of the solar system. Yep. So in particular, this Nature paper by Lascar and Gastineau, they integrated something like 2,500 solar system integrations. Okay. And they changed the orbit of Mercury very, very slightly. We're really within the uncertainties on its position. So they integrated these models of the solar system, and even within this small uncertainty found, of course, a great chaotic divergences in the trajectories of the planets. Yep. And it found some sort of estimate that at about 1% of 1% of simulations of the solar system will go unstable under what the current conditions of the solar system are. Okay. So we ran 96, sort of like, is it a shot in the dark? We're going to get that 1 at 100 that goes unstable. Right. And alas, we didn't. And so it was sort of like, that's fine. It's, statistics, but that was sort of our motivation on sort of giving us a baseline test to see where we're at.
Cool. Very good.
Yeah, so we ran them for 5 billion years, kind of like the previous integrations had done by Lascar. So our setup, we used rebound since it's sort of that's certainly my advisor's, pet love. And I know others like Konstantin Batygin also really like rebound, and it's been becoming quite popular, and it's nice. It's really amazing to work with Hanno directly on such a project. So we set it up using rebound, and we go through a bit more like explicit detail here about like what we're trying to set up. And we do share our code specifically on how we did this. But that is basically the point that we were looking at sort of was to achieve a high accuracy. We employ 17th order symplectic correctors, which have been in rebound for a while. They're an interesting way of when you split the Hamiltonian to do the integration, you can use these correctors. You can sort of tack them on the front and on the back, and they do this correction that doesn't cost it doesn't cost that much time because it's a little bit of computation on the front and at the end. So over a 5 billion year integration with trillions of time steps, these two little endpoints do very little to come for the time cost. But then this new thing that we did was we used the lazy implementers kernel method, which is compatible with general relativistic corrections. And this, we go into detail, and we mentioned it there in our 2019 paper, that it has all of these leading error terms. And we had investigated how different types of correctors change these error terms and what sort of benefits that gives you in this previous paper. So we're sort of like quickly summarizing what we did here, and that we chose this time step. And
8 days.
Yep, about 8 days.
8
and
days.
so then we go ahead.
Integrate that out for 5 billion years.
Yeah. So we it's quite a number because it's like about 10% of Mercury's orbit. So sort of why we chose 10%. We don't have even with all of the precision that you can get, there aren't actually very many. There's not a very large range of time steps that you can actually really choose that gives you any benefit. You can go from like 10% of whatever the smallest time scale is usually kind of like the highest you can go reasonably. And then if you go down to 1%, then you're sort of getting on the other end of well, now you're taking too many time steps, and it's in the long term not going to give you much trade-off. However, the downside is that if you keep such a large time step, if you have planets that start trying to get high in eccentricity,
Oh, right.
then your time step might not give you a nice spot. If you pass by, say, the sun or another body too quickly, you might not resolve that very well, and then that will not give you a very accurate outcome. So
Yep.
we do give a warning to say that if you're going to keep a fixed time step of such like 10% of the smallest time scale, then you should be sure that if anything is going out or like above 0.4 eccentricity, then you should be more careful about and scrutinize what you've done following that point.
Okay. Cool.
Yeah. And we use NASA's data. I know there's also other ephemerate data from the observatory in France that Lescar likes to use, but we use that one. And we also use the GR potential since it's the solar system. So the effects of general relativity are very important, but they're not the dominant. Yeah.
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 Cool.
And go ahead. Yeah. So one of the important things about the GR is one of the things that Lescar showed in his Lescar and Gastineau showed in their 2009 paper, that they did 250 integrations without any GR at all. And they found that about 60% of those simulations had an unstable Mercury event.
Okay.
And so when they included GR, like a GR correction, then only 1%. And so that sort of shows and points out that like the precession of Mercury, that rate of precession is quite significant to the stability of Mercury in the solar system.
Cool. That's interesting. Very good.
Yeah, and then we also talk a little bit about how we perturbed it, and it's the same perturbation style that Lescar did. So we were trying to match Lescar. There was, I mean, he's accepted quite a bit as quite authoritative in the field, and so we're not trying to question what he's doing, but we wanted to set a baseline to say like we believe Lescar is right, so let's do something to see if we also match in Lescar, and that's what we've done. So
cool. That's that's an amazing perturbation of measured on the scale of millimeters.
Yeah, that's sort of what like the interesting thing about the 2009 Lescar paper is that it's like these are measured in millimeters, and we followed the same just a perturbation pattern, and so he goes up to 2,500. So we have 750 there, and I think he goes up to like 1,200 or 2,500 times 0.38 millimeters, and really like you're basically on the scale of a meter, or 5 to 10 meters at most. And yeah, that kind of difference in measuring the location of Mercury, and then to say, okay, let's move Mercury by 1 meter on like a fourth of it, like a half of an AU, is so small, and it's like it's so easy to just miss that as a measurement, or just make that as an incorrect measurement or an uncertainty.
Right.
And we get such totally different results in the end. It's quite fascinating.
Where does the unit of 0.38?
I'm honestly not sure. We this was like a lot of my work that I was like doing on trying to reproduce what Lescar had done, and he used 0.38, so I used 0.38. I'm not really sure where it came from.
Where does that come from? Okay. Yeah. Very good.
I mean, it's a small value, and so it points out that this is small things. Okay. It could be his 0.38 is really close to the scale of AU. Like maybe that's where it came from.
So maybe it was chosen for stability purposes, right? Or for the finite precision of the arithmetic or something along those lines.
It's possible.
Anyway, it's something for me to look up. Anyway, carry on.
Yeah, no worries. And yeah, we use the simulation archive method to store the data, which we end up using to share the data. And it's something that Hanno and Dan Tamayo had created when Dan Tamayo was a postdoc at the University of Toronto. So it stores it in binary, which means that you can like look at it on any other computer and run it, and it'll be exactly the same as if you run, which is great for reproducibility. There's a pretty long history of code being really difficult to reproduce on different computers based on the number of compiler flags or which compiler flags you did or didn't use, and a whole bunch of other technical stuff that I know Hanno has focused really hard on making sure that integrations and rebound are reproducible across machines.
Good. Yep. Yes, I'm familiar with that. Yep.
Yeah.
Cool.
So yeah, then we decided to share the data for everyone. And part of the reason behind that was Scott Tremaine moved back to Toronto, and he was talking with Hanno, and he said, "Hey, Hanno, do you have any, simulations on hand that where I could get an idea on the the trajectory of Mercury's eccentricity over time or something," which we'll get to in figure 1. And so this is basically what motivated. So Scott Tremaine basically motivated us to get this put out for everybody, because he wanted to do it for a simple plot. It wasn't, it wasn't substantive, but I mean, it does take a long time to run. They take like 22 to 30 days to run a single simulation. And so if you want an ensemble of them, you need a lot of cores. It's just a lot of work. And so we thought, if somebody wants to just make some like vanilla basic plot from data from the solar system, we don't really want somebody to have to rerun it, because we have the data, it's sitting here, and we aren't using it for anything specific. So we thought we would just share it.
Cool. Very nice. All right. And then we have an example, let's say, of figure 1.
Yeah. If you want to zoom in on that, we could.
Oops. I don't want that. I want this.
The high resolution.
Yes, high resolution. That's what I want.
Yeah.
Okay.
Yeah. So this is not a super complicated plot, and it's kind of typical for showing long-term simulations of the solar system. You can see in the top panel, like the first sort of 100 million years, all of the trajectories of the eccentricity of Mercury basically overlap. So this is sort of saying, like, this point here, we have chaos in the system, and we can see it later, but at the beginning, this is where all the trajectories are sort of following along with each other.
Yep.
And then we, after enough time has passed, we get that exponential divergence, and the trajectories of the planets diverge substantially. And in this case, we sort of get this nice spread, which sort of gives us like a nice idea on, like, over 5 billion years, what's the kind of range of eccentricity that Mercury is going to go through, that it could go through. Right now, like present day, it's like 0.25 or 0.225 or something. But it can easily go up or like go down to lower values below 0.1 or even up to 0.4.
Yes.
It sort of gives us, and you can kind of see in the middle around 2 billion years, there's this brown line that sort of spikes up for around 2 billion. It hangs up there for a little bit and then spikes down. So there's a lot of dynamics going on in the solar system that, many people study and write papers about, trying to unravel what dynamics are important, what dynamics cause these sorts of effects. Because it could have, like, why did the eccentricity of Mercury rise so sharply? I mean, it's kind of a long time period. It's over tens of thousands or hundreds of thousands of years where it rises. Yeah. But then it just plateaus, and then it goes back down. And there's a bunch of stuff about secular resonances and other sorts of dynamic resonances that people investigate to try and explain why these things happen, and how they're related to the stability of the solar system and so many different things. So that's sort of the top panel, and kind of it captures sort of the dynamics of the solar system, since Mercury is the most likely to go unstable, since it's in the most eccentric and most inclined orbit. And it's also quite small. It's
light, yes.
Yeah. So it's really easy to kick and move around by the other planets. So it sort of gives us like a quick overview of how the dynamics of the system unfold. And then the bottom plot sort of gives us to make sure that our integrator is working nicely, to show us that our energy level is not going out or above. That it's sort of been the standard way to say, hey, look, this integration was reasonable, because since the Hamiltonian that we're modeling or using to model the solar system conserves energy, then we expect our integrator to conserve energy. And so we see here that it does conserve energy. It doesn't We get some nice low dips where we're getting closer to the original value, but it never goes beyond 10 to the minus 8. So it's nice that it stays low and stays good. So
Cool.
we sort of give it a trust rating.
The black line is average.
Yeah, sorry. Yeah, it's the average of the 96 simulations. So,
and let's see, 10 minus 12. So these calculations are done in double precision.
yes, in double precision.
Okay.
Yeah. I mean, I would love, I think a lot of people in the scientific community would love some computers with higher precision than just double precision. But I think until you can convince the game industry to have CPUs that require 128-bit or 256-bit
in
architecture. In hardware.
It's not that you can't do it. You can do it in software, but on board in hardware, yes.
Yeah, it would be nice, but I don't think that's going to happen anytime within the next couple decades. I think because you can get by in software, you can replicate higher precision in software, but it's much more expensive and much slower.
Yes.
Expensive in terms of time. Not
Right.
So yeah. And then we just leave a bit of a thank you at the bottom. We're always extremely grateful for the open source projects of Jupyter and IPython and Matplotlib. There's so much that we wouldn't be able to do, but that we can do because of them. And we do make a note to say, like, look, this took a lot of computation time, and we put a lot of CO2 in the atmosphere, probably doing it. So we, if you don't have to do it, you can just download it straight from Zenodo.
There you go. You can be a responsible citizen by not replicating unnecessary things.
Yeah.
Cool. Very cool. So I do have one question, and one reason this one caught my eye, which is the title, and you used it once or twice in the article as well, is vanilla. Vanilla, at least of the common spices, is the second most expensive spice in the world. Saffron being the most expensive. And so I'm kind of, we use it as though it was very commonplace or, laissez-faire, but vanilla itself is actually a fairly expensive spice. So what did you mean by vanilla integrations as opposed to, let's say, a chocolate or a strawberry integrations?
Yeah, I think we definitely use it as a colloquial term in terms of that. Like, we hope that it was sort of clear that vanilla was sort of bland or boring in a sort of way, as since vanilla ice cream is sort of the baseline. Mm-hmm. You take some vanilla ice cream and then you add things to it. And that's sort of what our thought was. But I do agree at the same time, having not thought about it till 2 seconds ago, that it's not always open to everyone. Like, it is a lot easier to access data and download it than it is to have computer time that you can just leave a computer running for a month. It can be quite expensive and unavailable to some people.
So there you go. There's gets into the expense part of vanilla. It does work. It does work. Very good. Cool. Garett, let me ask you, where do we go from here, given this research note? I imagine some of this might show up in your thesis at some point, but are there, for example, additional simulations that one may put into this repository? Might the repository open up for other people to put their solar system integrations for comparison purposes, ease of comparison purposes? So just sort of where do we go as a community, say, over the next 5 years on this project?
Yeah, I think there's a lot of space. I don't know in terms of hard drive space or disk space, but there's definitely a lot of space for sharing the raw data of simulations that are run. I know it can be quite difficult. Like, even just 100 simulations that we have, like, really we're like up there at 120 or so gigabytes of data, which can be a lot, especially when sometimes you buy a modern computer and they only give you 128 or 256, some small amount of gigs of data space. But I think in the future, I think there's a lot of space for people sharing the code that they use to produce their simulations and the code that they use to analyze their simulations. Mm-hmm. And as well, for simulations that have had different effects added onto them. Ooh. So, so for these vanilla simulations, We use general relativity since it's a super important factor in the evolution of the solar system. But someone might come to me and say, hey, Garrett, what about solar wind, or what about tides? There's so many other things that it's much more difficult to inject like those effects straight onto the dynamics, and you sometimes have to integrate them with the dynamics of the rest of the solar system. And then that gives us sort of a baseline of say, okay, if we start with just general relativity, or like a potential general relativistic potential, then we can see like if we started them in exactly the same way, because we can, because we shared the code, like we shared the starting point. So same initial conditions, same location, and then say, let's turn on this effect here, let's turn on this effect here, and we can watch those trajectories and see how they change, how they diverge, and what sort of differences we get.
Cool. Very nice. Very nice. Garrett, I want to thank you so much for walking us through your very lovely research note.
Thank you, Frank. It's been an honor to talk about it.
It's great. And thank you everyone for listening in, and I hope this made your astronomy day just a little bit better, and we'll see you on the next one. Thank you. Bye-bye.